Good evening, everyone. Hope I am audible on the other end. Can I just get a confirmation from anyone that they can get me?
Good evening. You are audible on the other end.
Thank you. So my name is Tutor Marius, and I will be taking you in math and physics. So please feel free along the way if you have any questions, even as we get into today's lesson, you are free to ask. And even outside, you're free to contact me. You can check out other videos uh, posted. I think I think the links to the YouTube pages, YouTube channels was shared, so you can check out Math with Marius, and yeah, you'll find video content there on math and a few on physics as well. So I'll take you in those two. And today we'll begin with math. And as we're starting math, we are going to look at set theory. Okay, let's dive into our lesson. So our content, what we will look at in this class, we're going to look at definitions, then we'll look at notation, representation, and classification. And all these are just all based on sets. So let's dive in. Uh, what is a set to begin with? So we have this definition here given to say a set is a collection of well-defined objects called elements. So a set must have objects and of course should be well-defined, these objects, and we just call these objects elements. So that's the simplest definition of what a set is. Uh, we have an example here. So the example says a collection of short students in a class. So the example here was trying to just ride on the point where we're saying um, must be a collection of well-defined objects. So when we say a collection of short students in a class, so short students in itself is not well defined because how do I know that somebody's short? So it is subjective. You have to really give a specification to say, okay, people that will be considered short maybe are people that are under 1 meter of height. So when you look at the second here where we have number two, it says a collection of students whose height is less than 1.51 meters. So here, this is more well defined. You can be able to collect this data here or collect those elements there because anybody who be less than 1.5 meters, meaning is what is going to fall in this category. So if we're to make this the first statement to be so well, saying short students, maybe we would say everybody who is below 1.5 meters is considered short, and you make what a collection of that. Then it will be what? It will be well defined. So this is just simply what a set is. Okay, now let's go straight into looking at the notations that we will use in sets. So the notations we have that a set will be denoted by what? By a capital letter. So we have the set A, set B. You see a capital letter, maybe C. All these here will just what? Will just denote a set. Then the elements of these sets will be denoted by what? By lowercase letters. So we have A, we have B, we have C, we have D. Like, yeah, there can be numbers as well. Two, three. So when we talk of the uppercase letters, these will be denoting the set. Then the lowercase letters will be used in the what? These will be the elements of that set. So if we say let A be a set, then let X be a member of what? X be a member of this set A. So if X is a member of this set A, we denote this as X being a member of A. So this is how we denote that this element X is a member of what? Of the set A, using this symbol here, which means a member. And if it's not a member, so if it's not a member, uh, let's say Y is not a member, we'll cross it like that of what? Of A, meaning the element Y does not belong to the set A. So this is how we are going to denote our sets. Okay, another thing that we will look at when we are dealing with these sets, so sets can be listed or can be given using a description. So I can give a statement maybe what why maybe to say my set contains even numbers. That's a statement. Or you can actually list out that set of what of the even numbers. So now when we're listing, our set is given in what? In a pairs of braces. So these are the braces. They'll look something like this. So inside here, we list our elements that are in that set. And at sometimes we will use what we might use parentheses like this. So it can be like that. Or we can also use you can see square brackets being used as well to denote what some sets like this. So these here will be some of the symbols that will be used as we are going to denote these sets. Okay, so that's about the notation. Now we have these here, which are just examples that are based on the same notation that we're talking of. So if you see the first one here, we have A, and A says top 10 selling fruits in what? In Zambia. So this is a description that is given, and it's given in what? In words. Then you see that part B here has what? Has we've listed out. So we've listed out there's 1, 2, 9, and 10. So that's listed out, and we're using these braces that you're seeing here, as we say that we will use braces to list down those sets. If you can see part C here, part C is given in what we call set beta notation, which we'll further look at in this class. And we see the braces are here outside. They are starting like that. And yeah, the description of whatever is inside is given there. And on the other end, we see that there's a square bracket here, and we have a, a, a parenthesis that is what? That is closing at that end. So when we look at that there, uh, the square bracket, this here, which is given at the end, is what we call interval notation, which we'll further look at as we go deep into set theory. But yes, so here we are using that square bracket and the parenthesis on the other side. Okay, so now we we can also see on this part D that we still use the same notation, and we have these parentheses that are given like that. So this is how we will denote what? We denote our sets. And yeah, there can be a description given, there can be a listing and all those things. So this is how a set will look. Okay, further on, we continue. We have this part here where we're going to look at the representation of what? Of the sets. So as we are dealing with sets, we can represent sets either in roster or tabular form or in set beta notation. So roster or tabular form. So roster or tabular form is just a form in which we list out these elements. So we'll be listing out these elements. For example, if we have a set A, I have a set A, and to list out this, I'll be listing out, let's say, it's a set of numbers. It'll be numbers from 1 to 4. So 1, 2, 3, up to 4 like that. So this is a roster form we're listing out. You can have a set X like this, and this set X can have elements that's A, B, C, D, and all the way up to there. So they continue like that. And then we can have another set that is maybe set B. Set B will have, let's say it has these elements A, E, I, and what, and O, which is just the set of what? Of vowels. So we can see that we're using these braces which we're talking of, and to denote the set, we've used the capital letter, and then To list these elements, we've used the lowercase letters. So this is a form of representation of the set, and this is called roster or tabular form. Okay, another form of representing sets is the set builder notation. So set builder notation is a form of representing sets by describing and stating the properties that satisfy the element, a given what, a given element. So now that is given, for example, we say we have our set A, and we're saying A is equal to, so it's going to have a general form where we have, let's say we're talking of X, then we have these two dots here, which is going to mean such that, and then you talk of something in terms of X describing a property of X. So our our element X has the property, let's say it has a property, then or you state the property that what this element X has. So this here is how we generally use set builder notation to describe whatever we're going to describe. So it's a set of what, of OX. So as you're reading this, you read set A is a set of OX such that X has a property P of X. So this is how the set itself is what is described. Then we can look at this maybe to look at a less more arbitrary example. We have, let's say we have the set B, and we're saying B, so is a set of OX such that then we're saying X is, maybe let's say X is an odd number. X is an odd number. So this here, we've described the property which we're talking about, that X is what is an odd number. So if I'm listing out, if I was to list out the elements of this set, I only have to list down what, the odd numbers. So that's how we describe. And you can see another notation as you're going forth. Let's say you have Y. Instead of writing this s- writing this such that as these two dots, others just used a line in between and to say Y such that Y, then describe the property. Let's say Y is what, is a medical student. Let's say Y is a medical student at Levy. Let's say it's a medical student at Levy. So this here is how you can describe or use set builder notation. Okay, let's just go into examples such that we see how to work out. Okay, so we have this part here, and we're being told the question says represent the following sets in roster form. So roster form is a listing form. So we have set A, and set A is given. So they've given this in set builder notation, and we have to write it in roster form. So it says X such that X is is a positive even number and less than 12. So the set here, or this entire set A, we're being told it's a set of OX such that X is what, is a positive even number and it's less than 12. So to list that out, so meaning we are talking of what, even numbers, and it has to be positive and has to be less than 12. So to start uh, to start with positive, so here positive even number. So even numbers are numbers that are what, divisible by what, by 2 and leave no remainder. So you have numbers that's 2, 4, 6, all the way like that. So they continue to go. So now to list this, we'll continue listing, but we list up to those that are less than what, that are less than 12. So the smallest meaning even number that we have is going to be what, is going to be 2, because they've said it has to be positive. So we have 2, we have 4, we have 6, we're going to have 8, 10, and we can't write 12 because they've said the even numbers are less than what, 12 in this case. So we could only add 12 if they had said that they are less than or equal to what, to 12. But then we see that it is not equal to 12, so we'll close our set here. So this is how we list down the first one. Okay. If there are any questions, as I said, feel free, even as we continue. So The second part says it has X such that, so B is a set of OX such that X is an integer, and we are saying X is in between -4 and 8. -4 and 8. So an integer. So when we talk of an integer and it's represented, so we know we can write a set of integers like this. So integers are just positive and negative what? Natural numbers. So the positive and negative natural numbers, when we talk of natural numbers, are numbers that we use to count. So those are numbers like 1, 2, 3, 4, 5. Yes, all the way like that. Those are natural numbers. But then when we talk of integers, meaning there's same numbers that we have like 1, 2, 3, we also have what? The negative version of these, that's -1, 2, -2, -3, like all the way, and this also all the way, but also including what? 0 is going to be part of this. So this is how this set is going to be. And they're telling us that then X is in between -4 and 8. So where there's -4 here, there's just a less than sign here, and there's no equal to sign like we have on the other side where we have what? We have 8, which must mean that -4 is not part of our set B, but 8 is part of our what? Of our set B. So to list this out, meaning we won't include -4, we have to start from what? -3. So we have -3, -2, we have -1, we have 0, then we have 1, 2, 3, 4, 5, 6, 7, and we have 8. Okay, is that a question? Okay, guess that's not a question. So if you're not asking a question, you can just mute your mic. All right, so we'll continue. So this is our set B, and this is what listed in the set B. Now let's talk of the other set which we have, set C now. So set C, they're telling us that it's a set of OX such that X is a two-digit number whose sum is 8. So it's a two-digit number, and its sum must be what? Must be equal to 8. So now we must look at the numbers and how they what add up to 8. So two-digit numbers that will start with what? With 8. And this is going to be straightforward because when you begin, you'll be like, okay, let me say I have 1. Then the other number that you need to add here to make this 8, just subtract this 1 from 8, and you know that you're going to have what? 7. So 17 meaning is what? Is the first number that you're going to have. 17 is the first number because when you add 1 and 7, you get 8. So the next thing is you just start increasing on this right number and reducing on the left number, which is 7. So if I increase on the right number, I have 2 there, increase, I'll just get 2. Reduce the other one, 6. This when I add, I get 8. Do the same, so I have 3 there, and what am I going to have? I have 5 there. Do the same, I'm going to have 4, 4 there. Increase there, I'll have 5, and I'll have 3 there, 6 there, and 2 there. Then I'll have 7 there and 1 there. So this here is the set C, which is just a set of X such that X is a two-digit number whose sum is 8. So this is how I list down or represent everything in roster form. Okay, we move on to the next question we have. So the next question says represent the following set in set builder notation. So how do we do this? We have to represent these in set builder notation. So we said as we are representing, we can represent them by description or you can use some notations even as you go on. So we have the first one, set Y. So look at set Y, starting 2, 3, 5, 7, 11, 13, and all the way. And they're showing you these dots just mean that this set continues to go up to infinity. So we will look at what that is supposed to mean. This is a set that continues to go like that. So now, if you observe the pattern, of numbers here, you notice that these numbers in the set Y are prime numbers. They are numbers that are just divisible by 1 and the number itself. And with prime numbers, when I divide, so for example, let me use 3. 3 is a prime number. So 3 is divisible by what? By 3. It divides into 3. How many times? Once. And then it's divisible by what? By 2. By 1, I mean. And it gives me what? It gives me 3. So these two numbers, when divided into this number, I should be getting that if I divide into 3, I'll get, if I divide the number into itself, I'll get 1. And if I divide 1 by into that number, I am going to get what? That number. And I should not get anything else. So that's the reason why when we look at numbers, let's say -3. So is -3 going to be a prime number? So the condition is it should be divisible by what? By itself, and it should be divisible by what? By 1. So, and it should give you that when I divide, it should give me what? 1 if it's divisible by itself, and if I divide it by 1, it should give me the number itself. So now, if I divide this by 1, this divided by 1 is going to give me what? -3. Of course, it's given me the number itself. But if I divide this by -3, so -3 divided by -3, this just gives me what? +1. This gives me what? This gives me +1. So I see that uh, when I divided this by this when I divided by it, it gave me this 1. Then when I divided by the other one, it gives me -1, -3. But I can also divide this by another number. So if I divide this by 3, it's going to give me what? -1, which then breaks the entire thing where we are saying that it should only be divisible by the number and what and itself. So we can only have positive prime numbers. Okay, so the discussion is not really about prime numbers, but you can look that further on. So how do we write this in Z-beta notation? So in Z-beta notation, we are going to represent this as, so the set Y, okay, is going to be a set of all X. So you can just represent it by X, saying all X such that X is a prime number. You can write this description here, prime number. X is a prime number. So, and you close there. So X Uh, Y is the set of all X such that X is what is a prime number. That's the first one. Number 2, you have Z there. So Z, you have R, A, E, O, U. How do you represent that? So you can say X such that X is, that's also another description you have to give. X is a vowel. So such that X is a vowel. Because when you look at those there, we're having what? Vowels. So somebody is able to list this set easily. Then the other one, we have E there. So notice it's from negative what to 3 there. So if I was to write this, I'm going to write X such that. So I can write it where I say, and when I look at these here numbers, these are integers that are listed in this set E. So I can write to say such that X is what? A member of what? Integers. First of all, I should state that it's what? A member of integers. Then I should state at what interval is it what? Is it valid? So that's from -3. So like that, and X is between -3 and what? And 3. And this -3 and 3 are part of what? A part of X. This is 3. Then close there. So this is how my set is going to look. I can also write it, let me write it in another form. So the math just has to be correct. Like it has to describe whatever you have there. So you can write it, you can choose to write it like this. It would be the same where somebody says X such that, and they state first of all to say that X is in between -3 and 3. Then they say X is a member of integers like this. So it's still fine if you write it like this, or like if you write it the other way around. So this is still going to be what? To be okay. All right. I don't know if there are any questions. Okay, so we continue. Uh, so we have classification of sets. So when it comes to classification of sets, we're talking of sets to be in form of where we have a finite set and we have an infinite what? Infinite set. So a finite set is just a set. So the first one, which we're talking of, the finite set, is just a set whose members are what? Accountable. So if I can list down those members, let's say I have a set A, and the set A is equal to, set A is just equal to, let's say A, B, and C, and it closes like this. So this here is going to be what? To be a finite set, because I can count these elements in there. 1, 2, 3. They are countable. So it's going to be finite. And there's a there's a term that we must notice when it comes to what? To numbering, or when it comes to counting these elements of what? Of a set. So the number of distinct elements that a set has. So the number of distinct elements, like this one here, we have what? We have 3 elements here. So the number of those elements is called what? Cardinality. Cardinality of the set. So the cardinality of this set is just what? Of set A is just 3. So the number of elements in the set A is just 3. So it's a countable set. So you can count that. The cardinality is 3. Okay, so for infinite sets are just sets that uh, we can say they are unlimited. We can't count these. For example, if I start listing, let's say I start listing, maybe set B is a set such that I have 1, 2, 3. Then if I put these dots here, meaning this continues to go up to what? Up to infinity. So I can't count up to what? Infinity is not a fixed point. Like positive infinity or negative infinity, they are not fixed points. So we just know that numbers will continue going as long as you can still add a +1 to the previous number, meaning the number what will increase by what? By a unit. And you can continue doing that and we can't end. So this is going to be an infinite what? An infinite set. Now, we have these 2 questions here. So the questions just tell us to classify the following sets as finite or infinite set. So let's look at the first one. The first one says the set of natural numbers. So natural numbers, which can be represented like this, these are natural numbers, symbol for natural numbers. So is this going to be an infinite or finite what set? So this is going to be an infinite set because natural numbers and the counting numbers. So from 1, 2, 3, all the way, as we say it, up to what? Infinity. This is going to be, this is a set of natural numbers. And this here is what? Is an infinite set. So here this is infinite. Then we have the second one. Second one says set A is a set. We have x such that x is a prime number and x is less than 10. So x is a what? Is a prime number. So if it's a prime number, it only has to be divisible by itself and 1. So then they're telling us that it's less than 10. So we just list prime numbers that are less than 10. And if I was to list on those prime numbers, I have 2, 3, I have 5, 7, and that is it. Is there any other prime number that is less than what? Okay, I think there isn't. So we, yeah, so 9 is not a prime number, and also saying less than 10. So it ends here, meaning my set ends what? Ends there. Okay, so I can even close here like this. So this here is a finite set because I can count these elements. I have 1, 2, 3, 4. So meaning the cardinality of this set is just 4. So this is the cardinality. The number of elements in the set is just 4. Okay. Then let's look at J. So J is set of all x such that x is a member of real numbers. They're telling a member of real numbers uh, and they're telling us that it's in between 0 and 1. So in between 0 and 1. So if we to write a number line, right? So we have 0 here and let's say we have 1 here. We have -1 going this way, -2, and let's say I have 2 here, and this is going up to what, up to infinity, like that. So real numbers, for now, we just say numbers that are what, on a number line, and where these include all other numbers such as, so if I was to write down to say, okay, we have the natural numbers, and these natural numbers are a subset of what, of the integers, then we're saying the integers are a subset of the rational numbers, and rational numbers are what, a subset of real numbers. So meaning real numbers are made up of the natural numbers, the ones that we listed before, the integers. So integers, meaning both positive and negative integers. You have these same fixed numbers like -1, -2, going up to infinity, like that. Then you have the rational what? Rational numbers. So rational numbers are numbers that can be expressed in the form A over B, where B is not equal to 0, and these here are co-prime, meaning they do not have common factors. So the number must be able to be expressed in what, in that form. And meaning, if it's expressed in this form, meaning these rational numbers are numbers that are just fractions. For example, half and all these are what, fractions. And these can be expressed in the form of what, of decimals. So this is like 0. What, 0.5. And in between here, as we can see, so they've told us that it's between 0 and what, and 1. So 0 and 1 is in between here. Let me use another color. So here, in between, this is 0 and 1. So how many numbers are here? So if we were to start, there are a lot of numbers here. There are infinitely many numbers that are here. Because I can just say any number. If I just start, I can start, let's say, uh, 1. If I start 1, 1 over 2 is gonna be there because you have 0.5. I just keep on increasing the what? The denominator. If I continue to increase the denominator that I'll be dividing by here, it's just that it's going, my decimal becomes smaller and smaller and still is going to sit in between there. So I'll have a lot of numbers. And since I can always put my denominator, I can continue increasing my denominator up to infinity. Like infinity is not a fixed point, but I can continue increasing, meaning that I can have infinitely many numbers here. So this set here, J, is what, is an infinite set. So this is going to be an infinite set. This here is a finite set, as we said. So that one is an infinite word set. Then the last one is just a set X such that X is a member of, um, is a vowel of the English word alphabet. And of course, we can easily list that out. So we have B, English alphabet, vowels, that's R, A, E, O, and what, and U. So this here is going to be the set B. And I can easily count those elements. So this is a finite what? It's a finite set. Finite set. Okay. So that's it about an infinite and finite set. Other key concepts that we just want to stress out in this class is an empty set. So an empty set, by definition, is just a set that does not contain any elements. So it is empty. There's nothing in there. So when we talk of end, of course, it's denoted. The set is denoted like this. So, okay, not like that. So it's denoted like that. So this is going to be an empty. This is an empty set. And of course, it can also be written like this. Okay, it can be written like that. So that's an empty set. Uh, okay, so when it comes to empty sets, we have this here, we're saying this is an empty set. An empty set is a member of what, or is a subset of every set. So I've used the term subset. So a subset is just a set containing another set. For example, if I have this set here and that set there, so I have a set outside there, A, and I have another set there, B. So, and if I have, let's say, elements that are listed here, uh, okay, like that. So B is a subset of what? Of the set A, because it's contained within the set A. So this is what is a subset. So, and we denote, of course, a symbol of a subset. We say B is going to be a subset, denoted like this, subset of A. So, this is how we denote the subset. Okay, so empty set, an empty set is a subset of what? Of every set. Every set is what? An empty set is going to be a subset of what? Of every set. Okay, so that's it about the subset. Then we have the universal set. So the universal set is a set that contains all other what? Or other elements. All elements are what are contained in the universal set. Okay, so let's say we're talking of so like the previous example where we're talking of vowels. So we have the set A, B, okay, not A, B. So we have R, A, E, O, and U. This is the set B. Then the universal set, which is usually denoted as U, it's denoted as U, or at times denoted as what? As E. So this universal set is the set that contains all these other elements, of course, even other elements. So where did we get these elements from? We got them from the English alphabet. And the English alphabet is going to go from what? From A, B, C, all the way, and we know it ends up to what? Up to Z. So this here is going to be the universal set for this set B. So the set that contains all elements is what is the universal set. Okay, then the other key concept one has to look at, which as we come to the close of this lesson, is equal sets. So sets are said to be equal. Okay, so two sets are said to be equal. If we say, so set A, let's say set A and B are said to be equal, and we like denoting them as A equal to B, if and only if, so if and only if, A is a subset of B and B is a subset of A, then the sets are going to be what? To be equal. So meaning A is contained in B, and also B is contained in what? In A. So then sets are going to be what? To be equal. So examples of equal sets. So let me give an example here. So let's say we have the set. We have the set. I'll list it out: 1, 3, 4, and what? And 5. And we have another set where we have 1, 4, 3, and what? And 5. So if we have these sets here, so these sets here are equal because we see that they have the exact same elements. There's 1 in this set, there's also 1 in that set. There's 3 in this set, there's also 3 in that set. There's what? 4 in that set, there's also 4. There's 5 and there's 5 there. So we see that this set is a subset of this one and vice versa. So meaning these two sets are equal. Even when we say, let's say we have the set containing the letters, so it contains the letters. So I have these letters. Say the letters what? Silent. Says letters silent like this. I have a set containing these letters, and I have another set containing letters that is listen. Let's say listen like this. So this here is going to be what? These are equal sets because they have the exact same what? Exact same elements. There's S there. There's also going to be S there. So a set that is going to contain these, they are going to be what? To be equal because they have the exact same elements. So this is how, or this is when we say that elements are what? Or sets are what? Are equal. All right. So this is it about this introduction to sets and understanding set theory. Further on, we will go and we will discuss set operations and how to handle these sets, and also different things like that are very interesting, like the De Morgan's uh, laws and also other set algebra things that we'll discuss later on. All right, thank you guys for coming through. I don't know if I have any questions. Does anybody have a question?